Hello Year 12 and welcome to the fourth video for our fourth topic, that's 4 squared, on the normal distribution. We are looking at measures of central tendency and spread here. You know what? You learned about most of these in year probably 7. Okay, and not all of it has progressed a long way since then. So hopefully a lot of this is quite familiar, but well worth the revision. So, when we're talking about a typical score, we've got a data set, we've got this large group of data. Rather than looking at it all at once, we want to get some concise description of it, right? Which means simplifying it, which means losing some of the detail or granularity of that data, right? If I'm after a typical score from a data set, I'm after a measure of central tendency, and these are the mean, which sometimes we call the average, the median, which is the middle, like the median strip down the middle of a road, and the mode, which is the score with the highest frequency. So the mean, add all the scores up, divided by the number of scores. This funny little sideways capital M looking thing is the uppercase Greek sigma, right? Means the sum of, right? It's a little shorthand in mathematics for saying add all of these things up. So add all of the scores together, add all of the frequencies together, and divide the sum of the scores by the sum of the frequencies. That gives you the mean. It's good for continuous data. That's things that you measure, things that have units like your height or your weight. Okay, the mean is good for those because it tends to spit out, or it certainly has the potential to produce an answer that is a decimal, even a recurring decimal, right? Because you divide by something. Rightio. So that's the mean. The median, as we said, like the median strip or even a medial ligament in your knee or something, is in the middle. It's the middle score, perhaps. But if you've got an even number of scores, you don't have a middle score. And sometimes we say it's the average of the two scores closest to the middle. Really important that you put your data in ascending or descending order, that you have to rank your data to find the median. Also, I prefer to think of the median as a number, not exactly a score, but a number that separates my data set into a top half and a bottom half with an equal number of scores in each group. Now, this has a bit of a flaw too, whereas if I have an odd number of scores, well, to separate them, I take the middle score away and I don't put it in either of the groups. I take that middle score and I say that is my median. The concept of that is not universally applied, and be really careful when you are reading notes or watching videos or finding other information about the median, but more importantly, the interquartile range. If it's not an Australian source, there are slightly different interpretations of this, so be warned. But the median is the middle, right? It's usually self-evident, and frankly, our calculator, I will show you shortly, will calculate it for us. The median is good for continuous or discrete numerical data. Discrete things you count, like how many brothers you have, or how many days of school you've missed this year, right? Median is good for that. It's particularly good for skewed data sets. If we talk about things like, say, house prices in Maitland. Works actually, maybe Maitland's not good. If we talk about house prices in Sydney, maybe. House prices in Sydney, house prices in Newcastle, house prices, commonly used for house prices. House prices in Newcastle, right? That it's what we call a skewed data set, typically, because while there are a lot of scores, a lot of house prices that are fairly similar, there is a very small number of very high house prices, right? You've got a big house on 3 acres overlooking the beach at Merewether. It is quite a few standard deviations above the mean, right? And if we include that in the mean, in the average, when I add them all up and divide them, it can make that average appear a lot higher than what we generally consider to be a typical score. It can make that mean, when we say average, it can make it higher than nearly all of the scores in some cases, if the data is that skewed. So the median is good. We say it's the middle one, half are above this, half are below that. And finally, we have the mode. We don't use the mode a lot. It's the score with the highest frequency. It's good for categorical data. That is things like what suburb you live in. Right, that would be an example of categorical data, or what colour your hair is, because I can't really organise that data into ascending or descending order to find the median, and I can't add them together to get the mean. Right? I don't say that, you know, Rutherford plus Lochinvar divided by 2 equals Windella or something, you know. I can't do that. There isn't an average for categorical data. I can't add them together, and I can't necessarily really put them in order to find a median either. So the mode we use for that sort of data, which frankly we don't do a lot of work with because it's hard to analyse it. Anyway, they are our 3 measures of central tendency. Right, good for finding a typical score. Now, in addition to finding a typical score, I might also want to know, out of this data set, is, while this is a typical score, how typical is it? Right? Is there very much variation within the scores? Is this a typical score and all of the other scores are very close to this? Or are they divergent, diverse? Are they very spread out? And by saying typical, is this not really very typical of them at all, just more typical than anything else? Well, we talk about measures of spread, how spread out the data is, right? And our main measures of spread, the range, the interquartile range, and the standard deviation. We, of course, have been talking about standard deviation for a while, and that is the most complex concept amongst each of these. The range is merely the difference between the highest score and the lowest score. We talk about temperature range, perhaps, right? The hottest minus the coldest. Range, pretty easy to find. You do have to be able to find the maximum or minimum scores, right? But that's usually computationally fairly straightforward. After that, we have this thing called the interquartile range. The reason we introduce the interquartile range, which is somewhat more complicated to calculate, is because when I have, for example, skewed data or data with an outlier, that is, a score that's very much higher or lower than the rest of my fairly typical scores, then that really blows the range out. Okay? If 95% of my scores are really close together, but 5% are really far apart, then my range implies, well, it doesn't show what's happening there very well. It just shows the ones that are furthest apart. The interquartile range we calculate by finding the quartiles. We split our data into 4 equal groups. Remember I said before with the median that we split our data into the top group and the bottom group? Well, we do that again, right? For the top group, we split that in half. And the middle point of the top group, right, we're going to call, in fact, we call the third quartile, right, because it's the higher one. We take the bottom group, we split that in half, right? The middle of the two groups made from the bottom half is called the first quartile. We split into 4 groups, and the divisions in between them, we have the first quartile, the second quartile, or the median, and the third quartile. We split our data into 4 groups, each with an equal number of scores in each group. Right, 4 groups with an equal number of scores. The difference between the third quartile and the first quartile. Righto? So our data is, imagine this is my data set. Right? I split it in half here, and then I cut it in half again here, and in half here. Right? This here is my interquartile range. Right, this is going to work better with an example. And of course, you're probably familiar with this already. But that's how we find the interquartile range, is we find essentially the median at the bottom half, the median at the top half, and the difference between those 2 medians. It does ignore, pretty much, any outliers. So the interquartile range is good for that, for giving you a description of the spread, independent, by and large, of any outliers. Oh, what happened there? Zoom. I don't want to do that. Cancel. It's not perfect, and computationally fairly challenging, and it does ignore, pretty much, quite a lot of the data. It still doesn't include every score very much. That brings us to standard deviation. And we've talked about this as sort of being like, not exactly, but like the average difference between each score and the mean. Right, it does rely on every single score, right? It does rely on each one of them to produce the calculation. It's not exactly the average of those things. There's a little bit more to it to smooth it out. Also, maybe you've seen me use this little thing here, which is a lowercase sigma, for standard deviation, but sometimes I've used an S as well. They're not exactly the same thing. If you think of normal data, if we had some normal data, a small data set is unlikely to have anything with a z-score of, let's say, like 3 or -3. If I have 10 scores, I'm quite unlikely to have anything with a big standard deviation, because they're really quite uncommon. As my data set gets bigger and bigger, right, it can all be part of the same original data set, right? It's got the same mean and the same standard deviation, but as I increase the size of the data set, I'm more likely to find those scores with a bigger or smaller z-score, right? The really big ones and the really small ones. They're not really outliers as such, right? They still belong to the same data set. It's just they're uncommon scores. They're infrequent scores. So I kind of generally need a really big data set before they're likely to crop up. And this idea of a population and a sample standard deviation takes that into account, right? The population standard deviation says, well, this is all of the scores in the data set. They're all being used here, so there is nothing lurking in the shadows that's bigger or smaller. Whereas the sample standard deviation says this is only some of them, so there is a chance that there are some really big and really small scores that haven't been included yet, right? They won't be common, but they are still likely to be out there. So they work out slightly differently, right? We never used to teach the difference between them. It's just become a new thing, and it kind of complicates things a little bit. But anyway, hopefully the question will make it clear whether you need sample or population. I have an example here. It says calculate the mean, the median, mode, the range, the interquartile range, and standard deviation for each data set. Just to go through them. So, first of all, the mean. Right, I'm going to grab my calculator here. Yeah, here's my calculator. Now, I could just add those numbers together and divide it by however many we've got. I could do that. But you know what? I've got a calculator. And if I've got to find, for example, the standard deviation, it's going to have to go into my calculator anyway. So let's do as much as we can there. So I'm going to go mode. In fact, let's go second function, 9, 3 equals AC to reset our calculator. We're going to put in stat mode. And it's just single variable data here. Whoa, that's not what I wanted. Mode 2 for stats. So just option 1 there, single variable data. Okay, these aren't like coordinates or anything. I don't have to have it. So we've got this. Now I need to put my scores in. 4, 4, 4, 4. Right, there are 4 4s. There are a couple of 5s. There's a 6, a 7, a 9, and a 12. Right, quick look at that. Tells me my mean. What's my mean going to be? Something like 5 or 6. Something like that. Right, clear that. Now, second function 1. 4, option 4 here, and we know that 2 is the mean. So our mean is 6. The median, I could, oops, come back calculator. I could calculate the median this way, right? I know there are 10 scores actually, 1, 2, 3, 4, 5, somewhere in the middle there. So my mode should be, I've lost my calculator again. My mode should be 5, but let me just show you here on the calculator. Second function, 1. This option here, 5 min max. It's only on the newer calculators, right? Option 4 there, 4 is my median. Now, you can see, why do that when I can just count them along here? If you've got a decent sized data set, and if it's not organised in ascending or descending order, then computationally, it's quite labour intensive to put it in order first before you can find the median. And you can't find the median unless you've got it in order. So, if perhaps you are doing something else, and we are doing all sorts of other things here, this is a good way to find the median. So my median is 5. Next up, I need, so done and done, I need mode. Well, in fact, my calculator is not great for doing this, I don't think. I do have to have my data sorted out to do that. I need I need to know the frequencies of things I can see fairly easily. I've got more forwards than anything else. Righto. So my mode is 4. Right, they're my measures of central tendency. Moving along now to our range, right, in order here. Again, if you've got a really big data set and that min-max, it tells you the minimum and the maximum, and you could do one minus the other, that's fine. Oh, look, I'm going to save a bit of time here and say 12 minus 4 equals 8. Therefore, the range equals 8. Done. Now, interquartile range. Now, I said we need to take the middle of the bottom half, the middle of the top half. Right, so in this case, it's going to be 4 and 7. And our interquartile range, the difference of those is 3. But let me just show you again on the calculator. An option for that. We go second function 1, 5. Right, I want Q3 is option 5 there. Minus, come back here to 5, minus Q1. Right, Q3 minus Q1, that's how we work out the interquartile range. Equals 3. Equals 7 minus 4 equals 3. And our standard deviation. Now, it doesn't say one way or the other. We're going to assume then population. And it hasn't said that, and we're going to say this. Right, remember that's for population, S for sample. Population, standard deviation. Come back, calculator. Now, there's no working to show for this. The second function 1. It's here where we find the mean in option 4. Option 3 there, see the S, that was option 3, 4, equals 2.53. 2.53. There we go. Done and done. Let's try again with a slightly different data set. Now this time I have, right, this is not bivariate data, it's score and frequency. So this means that there are not 5 scores here, there are in fact 60 or something. So we'll need to reset here. Second function 9.3 equals AC, and back to mode, 2 for stats, and 1 single variable. And then we also need to go mode, careful here, 2 for stats, arrow, oh no, whoops, sorry. Second function mode to go to setup, arrow down. 3 for stat there, and 1, turn our frequency on. Okay, that's a fairly complicated step. Pause and rewind if you need to see that again. Now, when I go second function 1 to our data, here we go. Now I've got an X and a frequency, score and frequency here. So 10, 20, 30, 40, and 50 equals, now arrow and across. Easier to do one column than the next because the equal sign takes you down one level each time. So 1, that's fine, that's already there. Oops, not going to move on unless I type something in there. 14, 25, 13. You can see this is roughly normally distributed. 2, right? There's a lot more scores right in the middle. Okay, all of that's in AC, and back to these things again. So we wanted, first of all, the mean. 4, 2 equals. So my mean equals, was it 30 point? Oops, come back. Ooh, this video's getting out of control. 30.2. My mean is this, my median. Right, now looking at this, right, there's techniques for finding this, and I'm pretty sure it's going to be 30, but calculator makes life easier. Come on, calculator. Second function 1, 5, min max. A median 4 equals 30. Great. Our mode equals highest frequency is 30 there. Right, there's our mode. Our range is 50 minus 10 equals 40. Our interquartile range. Now, what are our quartiles? Again, this is where the calculator comes into its own. So back here, my interquartile range is 5. So it is Q3 minus here we go, Q1 equals 20. Straight out of the calculator. And my standard deviation, again, I'm going to assume this is population. One more to go. My standard deviation, second function, 1, 4, 3 equals 8.4. Rightio. Look, there's a heap of stuff there, and a lot of this you've seen before, but it is well worthwhile revising and revisiting it. I hope that all of this makes sense. If you've got any questions, ask me in class. See you then.